Let me ask you something simple but thought-provoking. When you push against a wall, why do you feel a force pushing back on your hand? The wall doesn't move, right? So, what's causing that sensation? This is exactly the kind of question Newton answered with his third law of motion, one of the most intuitive yet powerful ideas in physics. While the first law tells us what happens when there's no force, and the second law tells us what a force does, it is the third law that explains what happens in response to an applied force. It says that whenever one object exerts a force on another, the second object immediately pushes back with a force of equal magnitude but in the opposite direction. In short, to every action, there is an equal and opposite reaction. Let's now understand what this means in simple terms. Imagine object A exerts a force on object B. According to Newton's third law, object B exerts a force back on object A. These two forces are always equal in size but opposite in direction. So, if object A pushes object B to the right with 10 newtons, then object B pushes object A to the left with 10 newtons instantly. We write this as force exerted by A on B equals minus force exerted by B on A. These forces act on different bodies, which is why they do not cancel each other. They occur in pairs and are always simultaneous. You can never have one without the other. As you can see in the diagram, both objects are interacting and the force arrows point in opposite directions. Let's take a look at a simple but convincing experiment using spring balances. In this setup, spring balance A is attached to a fixed wall. Another spring balance, labeled B, is hooked onto A and then pulled. Here's the interesting part, both balances show the same reading. Why? Because when spring balance B pulls on A, spring balance A pulls back on B with an equal and opposite force. This proves the law in action. The pull on B is the action and the pull on A is the reaction. They're equal in size but opposite in direction. So even a spring balance can become a powerful physics teacher. Let's now apply Newton's third law to a very familiar situation, a book lying on a table. The book has weight, so it exerts a downward force on the table. That's the action. But the book stays at rest. Why? Because the table pushes upward with an equal force, that's the reaction. So, the book's downward push is matched by the table's upward push. The net result? The book stays balanced, unmoving. This simple setup, a book and a table, perfectly illustrates action and reaction forces acting on different objects. Newton's third law is everywhere around us, we just have to learn to spot it. Let's take a few examples. Push a wall with your hand, you feel a force pushing back. That's the wall reacting to your push. A boatman rows his boat by pushing water backward, the water pushes the boat forward. A gun fires a bullet, the bullet flies forward, and the gun recoils backward. In a rocket, hot gases are expelled downward, and the rocket rises upward in reaction. Each of these is a perfect action-reaction pair, forces that always come in twos, equal and opposite. Have you ever wondered how you walk? When you walk, your foot pushes backward against the ground, that's the action. In response, the ground pushes you forward, that's the reaction. Or take the case of stepping out of a boat. As you push backward on the boat to step off, the boat moves backward. Even in cricket, when a player catches a fast-moving ball, the ball hits the hand, that's action, and the hand applies an equal force back to stop the ball, that's reaction. These examples, walking, boating, catching, show how Newton's third law operates in both still and moving situations. Let's quickly review what we've discovered about Newton's third law of motion. To every action, there is always an equal and opposite reaction. These forces act on different bodies but are always equal in magnitude and opposite in direction. From firing rockets to holding books, from rowing boats to walking on the ground, the universe constantly works through pairs of interacting forces. And that's the beauty of Newton's third law, a law that governs everything from your footsteps to the flight of spacecraft. I hope now you truly appreciate how interactions define motion. See you in the next session where we dive deeper into the fascinating world of physics.